Okay, so we have four vectors, v1, v2, v3, and v4. We're supposed to find a basis for the subspace W spanned by those four vectors. So remember, the span of a set of vectors is the set of all linear combinations of those vectors. So a basis is the smallest possible spanning set. So a basis has to be linearly independent and a spanning set. Okay, so I have to be able to create the same space as v1, v2, v3, v4 does, but with as few vectors as possible. So I may not need them all. So the way I figure out which ones I need is I put them in a matrix. And I row reduce. Doing this with technology. Okay. And then I identify my pivot columns, right? Pivot column, pivot column. And those are the vectors from the initial set that I need, column 1 and column 2. So V1, so a basis for W would be just V1 and V2. So all the linear combinations of V1 and V2 is the same set as all the linear combinations of V1, V2, V3, and V4. So because it'll turn out, because V3 and V4 were free columns, they can be written as linear combinations of V1 and V2, so they're redundant. We don't need them. Okay, here I have a matrix A, and I want to find a basis for the null space. So it turns out that this is no different than finding a spanning set for the null space like we did in the previous section. Remember, the definition of the null space is the set of all vectors such that A times X gives the 0 vector. So I want to solve A augmented with 0. And I row reduce. And we get 1, 0, 0, 0, 1, 0, negative 2, 1, 0, 0, 0, 1, 0, 0, 0. Okay, so this, if I write this out as equations, it says x1 minus 2x3 equals 0, x2 plus x3 equals 0, and x4 equals 0. My pivots are this one, and this one, and this one, the first non-zero entry of each row. And so my free variable is just x3. So I'm going to solve this equation in terms of x3. And this equation for the pivot in terms of x3. And then if I put this in parametric vector form, my solution set, I need a vector for each free variable, which is only one. So x1 is 2 times x3, x2 is negative x3, x3 is the free variable, so x3 equals x3, and x4 is always 0. So my basis for the null space of A is just this vector. Basis for call A is the set of pivot columns from A. So to identify the pivot columns, you have to row reduce, and we've already identified them. pivot column, pivot column, pivot column. But then we have to take those columns from matrix A. So column 1, column 2, and column 4. So 1, 0, 3, 0, 1, negative 1, and negative 2, 4, 3. That's my basis for the column space. Okay, find a basis for the set G, which is the set of all vectors that look like A, B, 2A. So my basis might be 1, 0, 2, and 0, 1, 0. Okay, so how did I come up with that? So I rewrote A, B, 2A in parametric vector form, right? So I said this is 1, 0, 2 times A plus 0, 1, 0 times B. That would give me A, B, 2A. And then I picked these two vectors form my basis. Okay, consider the polynomials P1, which is 1 plus t squared, and P2, which is 1 minus t squared. Is P1, P2 a linearly independent set in P3? Why or why not? Okay, so remember that even though these aren't traditional vectors, when we learned about linear independence of vectors in Rn, we said if you only have two of them, it's pretty easy to tell. If one is a multiple of the other, they are not linearly independent. So is there some number I can multiply P1 by, some k, where I would get P2? And the answer is no, because to change this sign, I would have to multiply by negative 1, but this sign doesn't change. So P1 is not a multiple of P2, no matter what you pick for k. So these are linearly independent. One is not a multiple of the other.